Good evening. I hope all of you are there. We will have a brief discussion on this topic. We will continue this topic again next week or this coming Saturday because of the importance of this topic. We are going to deal with the cyclic voltammetry, which is one of the, I will not say powerful, but popular technique of electrochemistry. As you all know, cyclic voltammetry is voltage versus current. Many of the electrochemical measurements are voltage versus current only. Now, briefly recapping what we have done up to now is, we have first started with what are electrochemical cells. Electrochemical cells essentially consist of an electrolyte and two electrodes. And there can be varieties of the electrode reactions and other things we will see later on. Now, when we take two electrodes in an electrolyte, there is always an electrode-electrolyte interface. This electrode-electrolyte interface has a model. Okay, it can be model as a capacitor, or the ions are those things. But what is the problem here is, in a recent paper also I have seen that it is whatever we are drawing a model is only an ideal model. There is no real model in this, because the ions very near to the electrode are solvated to a different extent, and therefore the redox potentials and other things are changing. We will see what is the current status of this later on. So therefore, the models of electrode-electrolyte interface, even semiconductor electrolyte interface, is not fully understood still today. But still, we can approximate it to a capacitor or a capacitor with the solvation and other things. When we come to the electrode kinetics, what we are talking about electrode kinetics is the electrode reaction taking place at the anode and the cathode. So therefore, the difference between the anode and the cathode current is the electrochemical current. This is what is called the Butler-Warmer equation. Anodic current minus the cathodic current. Now, when we are doing these electrode reactions, we can use the electrodes in various ways. We can have stationary electrode, we can have rotating disc electrode, we can have varieties of electrodes. We will see later on what are the various varieties of the electrode. Okay, disc electrode, glassy carbon electrode, many electrodes are possible. So therefore, all these different electrodes, the transport of the depolarizer, the electrochemically active substance, because the electrochemically active substance must be capable of undergoing electrochemical reaction within 2 volts. Many of the many of the chemicals undergo reactions within 2 volts. So therefore, we will see later on why 2 volts limitation, because above 2 volts the electrolyte is dissolved in water and water will decompose. So therefore, the electrochemical reaction will be the water decomposition reaction and not the electrochemically active substance. That is why less than 2 volts is what is required. I hope you understand. Many of the electrochemical reactions are done in aqueous medium. We can do non-aqueous electrochemistry, but we will take it up later on. When we do non-aqueous electrochemistry, the potential that we can scan depends upon the non-aqueous substance that we are using. So cyclic voltammetry is in which direction of the potential is reversed at the end of the first scan. Thus, the waveform is usually the form of an isosceles triangle. The advantage using a stationary electrode is that the product of the electron transfer reaction that occurred in the forward scan can be probed again in the reverse scan. So therefore, even if you are missed in the forward direction, you will get it in the reverse direction. CV is a powerful tool for determination of formal redox potential. We have to define this formal redox potential. We will do that later on. I have already told you formal redox potential is not E0. E0 is a standard redox potential. E0 plus or minus RT by NF logarithm of activity coefficients of the reduced species divided by the activity quotients of the oxidized species. This whole thing is called the formal potential. Because we are assuming in many cases the activity quotients are unity and concentration terms are used, so what we are really determining is the formal redox potential and not the standard redox potential. Standard redox potential is when the activities of the reduced species and the activities of the oxidized species are unity. We'll have opportunity to talk about the formal potential equation things later on. So the voltammetry is comparison of voltammetry to other electrochemical measurements. Cyclic voltammetry is one form of voltammetry. Voltammetry is electrochemical method in which information about an analyte is obtained by measuring the current as a function of applied potential. Only a small amount of the sample analyte is used, so that the transport of the species to the electrodes are diffusion controlled. Now we have already talked about it, that it is normally done with a 3 electrode system. Working electrode is where the reaction is taking place. Reference electrode is the against which we are measuring the anode potential or cathode potential. Counter electrode is the where the completes the circuit. Supporting electrolyte is excess non-reactive electrolyte like alkali chloride, potassium nitrate, ammonium nitrate, like that. We will see later on what is the characteristic of the supporting electrolyte. They should have the transport number of the anion and the transport number of the cation must be same. We will see later on all those things. So therefore, what we are talking about in cyclic voltammetry is potential is swept as a function of time in a linear manner, and what we are measuring is current versus potential. Okay, potentiometry is measure potential of the sample or a system at 0 or near 0 current. Voltammetry measure current as you change the potential. Coulometry uses up all the analyte in process of measurement at fixed current or potential. Coulometry, okay, potential coulometry or amperometry, amperochlorometry, and that thing. Only voltammetry use only small amount of analyte while the vary the potential. So voltammetry first reported in 1922 by Czech chemist called Heyrovsky, in whose name the polarographic equation goes. Later given Nobel Prize for method. Theory of voltammetry is excitation source is potential excitation source. Please remember that. For example, if you want to make one person active, you have to excite him about what you are doing. For example, you want to ask him to come for a movie, you have to tell him that the movie is good and all those things. Then only, so therefore, so excitation has to be in any process. Excitation has to be there. For example, if you want to carry out the reaction at a specified rate, you have to increase the temperature. Temperature is the exciting parameter. So now we can do two things. Okay, the potential can be varied like this or like this. So the bulk concentration will vary like this. This we have already seen this. So we have talked about the transport of the species to the electrode. The transport of the electrodes can be turbulent or laminar flow or diffusion. What we are trying to do is diffusion current, because when you diffuse the current, the ions to the electrode, the electrochemical reaction is the rate determining step. Because in electrochemical reactions, we want the electron transfer reaction to be the control. So we have already talked about it, migration, convection, and diffusion. So we will not talk about them. Cyclic voltammetry is carried out on a stationary electrode, okay, not rotating disc electrode or any other electrode. They normally involves the use of an inert disc electrode made up from platinum, gold, or glassy carbon. Normally glassy carbon used, we will see later on. Glassy carbon is mirror-like carbon. Nickel has also been used. The potential is continuously changed as a linear function of time. The rate of change of potential with the time is referred to the scan rate, nu. This is an important parameter or important variable. Compared to the rotating disc electrode, the scan rates in cyclic voltammetry are usually much higher. typically 50 millivolts per second. This is the typical cyclic voltammetry scan rate. So we have seen when I take an analyte, for example, you take lead 2 plus ions, lead 2 plus ions will reduce at a potential E0 at minus 1.13 volts versus normal hydrogen electrode. Potassium ions will reduce to at 2.93. That is why we are using potassium nitrate as the supporting electrolyte. We will normally scan from 1 volt to 0 volt to 1.5 to 2 volts only. Electroactive species in the sample solution are drawn towards the working electrode where a off-cell redox reaction takes place. Another corresponding off-cell redox reaction will also take place at the counter electrode. The resultant current flowing through the electrochemical cell reflects the activity, the concentration of the electroactive species involved. So you can see the lead 2 plus is getting reduced while it is diffusing through the potassium ions. Potassium ions are moving towards the electrode, but it does not get undergo reduction because the potential is only minus 1 volt. What we need is minus 2.3 volts, 2.93 volts to reduce potassium ions. So potassium ions migrate. Large amount of potassium ions are present. Lot of potassium ions migrate, but layers of potassium build up around the electrode, stop migration of lead 2 plus ions via Coulombic attraction. Lead ions migrate to the electrode via diffusion. So the E applied is given by E0, the standard redox potential, minus logarithm of 0.0592 by N, RT by NF. Okay, we will later on show you how the value of R and T has to be expressed so that you will get 0.0592 by N. N is the number of electrons, M of the concentration of the reduced species by the concentration of the oxidized species. So this thing we have already shown. We are repeating that at this time, the cyclic voltammetry, the potential is linearly varying with respect to time, and current is varying exponentially with respect to potential. Measured current I is NFAD dCA by dCA by dx, where this ratio is the slope of the curve between C molar bulk concentration and C molar surface concentration. We'll see later on all these things. So therefore, I will be equal to NFAD by delta C bulk concentration Sir, only one person is other with others left. Okay. Then we will have it tomorrow. Tomorrow, okay. You send a mail to